Salutations, my fellow homunculi. This is 234 Palindrome linked list. This problem ain't too bad, not gonna lie. It's very simple to the reverse string problem. Very similar to the reverse linked list problem, if any of you have done those problems. But I'm going to show you an intuitive solution, not the fastest way you can do this, of course, but trash solution is best. You don't want to write a POG solution the first time around because you don't understand the problem. It's better to start with a bad one, increase your understanding of the problem, therefore the quality of your solution, and therefore the time and space complexity. But 234 palindrome linked list. Given a singly linked list, determine if it is a palindrome. Right? This is a singly linked list, which means there's only pointers going from, let me make this bigger, from the front of each node to the next node, right? There's no way you can go backwards, right? The only way you can go backwards is if you either reverse it, right? Or I'm not even going to say the other one because it might confuse you. But how would you do this, right? So forget the linked list for a second, right? Imagine you had an array, right? Also, let's figure out what a palindrome is, right? A palindrome is any string, right, that is the same forwards as it is backwards. So something like race car as a string. So R, race car, forward and backwards is race car. The same way that 1, 2, 2, 1 is the same forwards as it is backwards. So that's the idea here. So imagine, right, that you had an array, right, that was 1, 2, 1, right? How would you check if this array was a palindrome, right? Would you not just create a pointer at the front of the array, right? And then you'd create a pointer at the back of the array. We're just going to make this one an arrow. Actually, we'll just use 2 stars, right? Because you know the first index is 0, the last index is capacity minus 1. It will have just this one go up by 1 and this one decrement by 1, right? And then on each iteration, if they're the same, that's good. Then we'll move this up. Then we'll check these. These are the same. That's good, right? And then usually, right, you stop, which is why it probably would have been a good idea to change the symbol. Let's just use an up arrow now. Usually you know when to stop, right, when they pass each other, right? So when they pass each other, you know that they have successfully, that it is a palindrome, right? You successfully, or if it's the same, also the same algorithm to reverse a string, right? So reversing a string is also the same, right? Except instead of checking if they're the same, you would actually swap the positions, right? So how do you check if a linked list is a palindrome? So essentially you need a way to go from the front and the back at the same time and have them move to the center, right? But this is a linked list, so you can't do that. So a simpler solution, right, would just be to iterate through the linked list, append each value to an array, right? Then you would have an array of the same values. Use reverse algo above. Then you could just use the algorithm above, right? So this would be linear space, linear time. But I'm going to show you a better way to do it, right? Especially what's even better than the way you do it is the intuition behind how you solve it, right? So there's a better way to do it with the stack, right? And then I'm going to show you how that works, right, with this amazing work of art I just drew with my mouse, okay? So how does this work? So you have, for example, how does a stack work, right? So we have this guy here. He's pretty jacked, right? He has a pretty cool ear, pretty cool haircut, but he's kind of upset, right, because he's washing dishes, right? So how would you wash dishes? Imagine you were a dishwasher, right? And so you're washing dishes. And each time you're washing a dish, right, someone gives you a plate, right? But you can't take the plate on the bottom, right? Because if you took the plate on the bottom, all the plates on top would fall, and it would be a disaster. You'd probably be fired, right? I wouldn't be fired. But what you have to do is take the plate off the top, right? And so that's kind of how a stack works. It's a last in, first out data structure. So the item that was added last, which is this plate on top, will be taken out next, right? And then you can go straight towards the bottom. What's interesting, right, is if you're washing these dishes, you would notice that the first plate you were handed is actually the last plate that you wash. Why is that? To reiterate what I said, items are added on top and they're taken away on top as well. So the last item you do will be the first item. So where's the intuition for the problem behind this? If you're iterating through a linked list, you can actually just on each iteration just add the item to the stack, right? So if we start at 1, we're going to add it to the stack. 1. Next node, 2. Boom, next node, 2. Boom, next node, 1, right? And so if we had a stack here, so this stack of plates just became 1, 2, 2, 1, just to make it simpler. And I'm going to write it over here instead, right? To make it even more intuitive. Now, right, this was our first iteration, right? By iterating through this list, we were able to create the stack, right? Now what we can do is we can actually go back to the front of the stack, to the front of the linked list again, and just iterate again. Why can we do this? Because now our stack will actually represent the linked list, but in a reversed order. So now we can say, hey, is the first element in the linked list the same as the last element in the stack? Why would it be the last element in the stack, right? Because we said the first item in the stack is the last item in the stack, right? I guess this is a little bit confusing, but the first item in the stack, right, is the first item that was ever added. And the last item in the stack was the last item that was added. So if the last item that was added as we were iterating was this last element here. So we can now just iterate, right, through the linked list while popping elements off the stack. And if the most recently popped element is the same as the current element, right, then that's a check mark, right? And so we can just keep doing this. So we'll move to the next node. Is 2 the same as the second element on the stack? And we're just going to assume that we're popping this every time we circle it, right? It is. We'll put a check, right? Now we'll go to the next node. Is 2 the same as the next element that we pop off the stack? It is. That's dope. We'll write another check mark, right? Is 1 the same as the last element in the stack? The last element in the stack, which is technically the first element, right? It is, right? And that's just the intuition behind the problem. So there's a lot of different ways that you can use a stack to reverse something, right? You can use it to reverse a string, an array, a lot of different things. But with an array and the string, you can often do these in place, right? But it's just good to know that it's possible. This is one of those scenarios where it comes in handy, right? So now that we know what we're doing, also first time doing this problem, by the way, confirmed. Now that we know what we're doing, right? Now we just need to, what we need to do is just say, hey, we're going to write the scaffolding code to reinforce what the intuition, and then we're going to write the code. We're going to create a stack, right? So how do we create a stack? We can just create an array, right? In Python, this is how you would do it. In most other languages too, I think. Because if you think about it, an array and a stack are very similar, right? Except the fact that with an array, right, it depends on how you use it, clearly, but in this case, you can kind of blur the lines a little bit. If we use an array, right, and only operate at the end of the array, then technically it's functioning as a stack. It's a very simple functionality stack, though, so you don't want to go too far with it, right? But we can just kind of use an array and kind of use it as a stack. So we're only going to add elements to the end and pop elements off the end. So that's always going to be constant time, or constant time amortized if you're adding to the end. So we're going to create a stack, iterate through linked list, right? And we said on each iteration, add element, or we're going to say add val to the stack, right? Then we're going to iterate through linked list again, right? If stack.pop, right, which is going to be the most recent element, the last added element in the stack, equal to, right, ll.node or ll.val, which is the linked list, the current value of the linked list we're iterating through. That's dope, right? That means we're doing good. But they're asking us if this is a palindrome, right? So it'd be easier to just say, hey, if they aren't equal, right, then return false, no pally here. So there's no palindrome here, right? So if we make it outside of this linked list, if we make it outside of this for loop, so right, our only way to exit here, right, is if it's not a palindrome, right? So if we make it outside of this for loop without ejecting on this return clause, right, then we are a palindrome, right? Because we made it through, and every time items are equal. If they weren't equal, we would have quit, right? So now we can just implement that, right? So we're going to create a temporary node here, which we're going to set to head, just because head is kind of where the head of the linked list is. We don't want to iterate with head, right? Otherwise, we won't have a way to get back to the front of the list. So we're just going to use temp. We're going to say while temp is not none, right? We're going to l.append temp.val, right? Because it says that linked list node is defined up here as value and next, right? Now we can have to reset temp equal to head, right? Because temp is now at the end. And we're going to do the same thing while temp is not none, right? And before we write the if, we're going to say, oh my God, I almost forgot. Temp is equal to temp dot next, right? We actually have to iterate, otherwise this will run infinitely. Then we're going to say, hey, if, I'm not even going to call this L, I'm going to call this stack, just to be very, very literal. We're going to say, hey, if stack.pop, right, does not equal temp.val, right, return false, right? This is not a palindrome, right? And if we run this here, we'll see that this is the correct answer, right? And so what's the time complexity, right? So we're actually iterating through the list once here, once here. So if the linked list has n nodes, right, we're running in 2n time, right? So 2 times the number of nodes in the list. But 2n is kind of irrelevant, right? We always drop the constant, so this is just linear time, right? What's the space complexity? Well, we're allocating a data structure here, which is going to be a stack, which is going to contain just as many elements as there are in the linked list. So if the linked list has n elements, then our stack is going to have n elements, so this is also going to operate in linear time. And so that is palindrome linked list. If you want to improve on this solution, there's a couple different ways you could do this in constant space. You could actually drag the end pointer, right, all the way back to the front, and then you could iterate length of the linked list -1 times on the end pointer, and that's how you could also check. You can also do it in constant time by going through the list once, right, and then reversing it and then going through it again, how the solution does it. But this is a very simple solution, so you can iterate on it just so you can understand what's happening. But this is 234 palindrome linked list.